Okay, this is Math 105, Section 1.8, Part 1, or Part A. So we looked at points on a line before, and we call it in one dimension. We identified those with real numbers. So we looked at just like the variable x, and we formed our coordinate line with that. And we can do a similar thing with two dimensions. Now we're going to have two variables, x and y, and we're looking at points in a plane instead. So now we have a flat surface that's going back and forth. Like so. We're going up and down. We're going back and forth and up and down. So our x would be back and forth, and our y would be up and down. Okay, so we're looking at a plane, kind of like a flat surface, like a blackboard. Okay, so we're looking at points in a plane, and we use ordered pairs of numbers instead of just a single x or y. Okay, we're going to form our coordinate plane using those. Okay, or we call that our Cartesian plane. So when we talk about ordered pairs, we're looking at an x and a y, and they're going to be in parentheses, and the x always goes first. So when you talk about ordered pairs, you're going to have your x first and your y second. Okay, that's a y there. Sorry. Okay, so we draw two perpendicular real lines. The number lines cross, and they intersect at 0. Okay. One line is horizontal, and we'll call that the x-axis, and the other line is vertical, and we'll call it the y-axis. Okay, the points where those two number lines, the x-axis and the y-axis, intersect is called the origin. Okay, and that's 0, 0. That's right in the center there. Okay, and then we label our quadrants, starting with the positive quadrant where x is positive and y is positive. We're going positive on x and positive on y. Okay. So this is positive on x and this is positive on y. So we call this the first quadrant, and then as we move counterclockwise, we go in ascending order. So the next one would be the second quadrant. That's where x is negative and y is positive. Okay. The next one is quadrant 3. We're using Roman numerals here. That's where both are negative. And then quadrant 4 is where the x is positive and the y is negative. Okay. So that's where our quadrants, they're labeled 1, 2, 3, and 4 using Roman numerals. And just remember that we're going counterclockwise. Okay. Okay, so if we look at a point P in the coordinate plane, any point, we're using an ordered pair to represent that. So we're going to use an A comma B, where A is our x coordinate and B is our y coordinate. Okay, so we have to use two numbers because we have a left and right component, which is the x, and then an up and down component, which is the y, to get us anywhere on this coordinate plane. So you can kind of think of these coordinates of a point as its address. Tells us where it's located. So if the first one is 5, that means we're going to go 5 to the right, and then 0 is the second one, so we're not going to go up and down at all. So 5, 0 would be here. 1, 3, we're going to go 1 to the right and then up 3. Okay, starting at the origin. Minus 2, 2, we're going to go 2 to the left. Minus 2 is the first coordinate, and then up 2. For minus 3, minus 2, we're going to go 3 to the left and then down 2. So remember, the first one is always your back and forth. Okay, and then finally 2 minus 4, we're going to go 2 across and 4 down. Okay, so let's look at a quick example. First, we're going to look at, this is using set builder notation. Now it's the set of all x, y pairs. So we have x comma y in parentheses with that bar. So this is the set of all x, y pairs where, well, we'll go over to this one because we have a typo there, where x is greater than 0. Okay, so let's see what that looks like. So that's going to look like this. We've got, if you see, we're saying x has to be positive, so we're going this way to the right of 0, but we can go completely up and down because we're not making any restrictions on y. When we don't mention a variable, it means we can do whatever we want with it. So y can be whatever it wants, but x has to be positive. Okay. Now this should be dotted if it's greater than 0, and this should be solid if it's greater than or equal to 0. So technically, we should be writing it like this. I'm going to use the same notation. Okay. X, y, the set of all x, y, in parentheses, such that x, and I'm going to say greater than or equal to 0 in this case, because we can see that x is equal to 0, which is the y-axis, is solid. Okay, so we're going to put an equal to there just to make that correction. Okay, the next one, I just copied it over, is the set of all x, y pairs such that y equals 1. Okay, So we're saying nothing about x, which means x can do whatever it wants, but y has to be 1. So it's going to be just that line y equals 1. I should probably add arrows on the end there because it keeps going in both directions. Okay. So we just have that flat line there where we say y equals 1 when we're talking about x and y. Okay, in the third example, we have the set of all xy pairs such that absolute value of y is less than 1. Now remember, absolute value means distance from 0, so that means we're going to be less than 1 away on the y, less than 1 away from 0 on the y. Okay, so our interpretation of that is the absolute value of y is less than 1 if and only if negative 1 is less than y, which is less than 1. In other words, y is between -1 and +1. Okay, so the region will be those points in the plane where the y coordinates lie between -1 and +1. Okay, and then notice that we didn't say anything about x, so x can do whatever it wants. So we're going to have this region. You see where we're going forever in this direction. Okay, so I'll put arrows there to say that this keeps going. Okay, and this keeps going in the other direction, the right. Okay, positive direction. And then we have a dotted line on y equals 1 and a dotted line on y equals -1, and then we're going in between those two. Because if you think about it, there's 0, right? And in the y, you're always, we're talking about 0 in the y. This is y equals 0 is the x-axis, right? So if we're looking at y equals 0 and we go less than 1 away, we can go up to 1 up or down to -1 down. Okay, and we leave those open on the ends because we don't have an equal to there. Okay, let's talk about distance between 2 points. Now we know in one dimension the distance between points A and B on a number line is just, now that D means distance, is just absolute value B minus A, as we saw in a previous section. Okay, but now we're looking at 2 dimensions or 2 coordinates for each point. So if we have 2 points, let's say point A is x1, y1, and B is x2, y2, and we want to know that distance, that red. Okay, we can't just take the absolute value of their difference because we have 2 coordinates, right? In other words, these points don't line up perfectly, right? We have differences in x and differences in y. So what we do is we create a right triangle with those 2 points. We go straight down to the other point, and then we go straight across to the other point. So we have this right triangle with the 2 blue sides. Now the vertical side is just the absolute value y2 minus y1. It's the change in y. Okay, and then the horizontal is the absolute value of x2 minus x1. So we have these 2 sides of this right triangle. Okay, what we're going to do with this right triangle is use our Pythagorean theorem, which says a squared plus b squared equals c squared for a right triangle. Here's our right angle. These are the legs of the triangle, and this is our hypotenuse. So we have our Pythagorean theorem, a squared plus b squared equals c squared. And then we're going to apply that to find this distance, which would be our c of this triangle. Okay, so the distance is our c. Okay, x2 minus x1 is our a, so we have x2 minus x1 absolute value squared is a squared. y2 minus 1 absolute value squared is b squared. So there's our c equals a squared plus b squared square root. We're doing this. We got that by taking the square root of both sides here with our Pythagorean theorem. Okay, so that's how we get this here. Okay, so the distance is just the square root of x2 minus x1 squared plus the square root of y2 minus y1 squared. That's how we get our distance formula. So we can say the distance between 2 points is square root of x2 minus x1 squared plus the square root of y2 minus y1 squared. And we don't need to use the absolute value here because we're squaring it. So it doesn't matter if we use, we can kind of go without using the absolute value here because we're squaring it anyway, so it would become a positive by virtue of squaring it. Okay. So think of like this is the horizontal side of your triangle, we're squaring it. This is the vertical side of your triangle, squaring it. And then this is the hypotenuse, is that distance between the 2 points. Okay, so here's an example. We have point 1 minus 2 and P and point Q 8, 9. And we want to know which of the points of these points is closer to that point. Okay, now we could do that by plotting it, to point A, 5, 3. But what we can do is take the distance between these 2 points, P and A, and then take the distance between Q and A and see which one's smaller, right? So distance between P and A is x2 minus x1 squared plus y2 minus y1 squared, so 3 minus a minus 2 squared. This is 4 and this is 5, so 4 squared plus 5 squared. And then we take the square root of that, so 16 plus 5 squared is 25 plus 16 is 41, so we're taking the square root of 41 to get that distance between point P and point A. Now we do the same thing with Q and A. Okay, so we'll use this. This will be x1, x2. This will be I'm sorry. This will be x1, y1. This will be x2, y2. So our distance is x2 minus x1 squared plus y2 minus y1 squared. So that's 3 squared, or minus 3 squared, plus a minus 6 squared, which is 9 plus 36, which is square root of 45. And we can see that this distance is smaller right here. And here we can see, if we graph it, we can see that point A is a little bit closer to P than it is to Q. You see this distance is a little bit shorter, but we can do that absolutely by doing what we just did in the previous slide. We're looking at the distance formula to find the two distances. Okay, the next thing we'll look at is the midpoint formula. And think about 2 points. Here's x1, y1, and here's x2, y2. And we're looking for the point that's halfway between those 2 points. Okay, so here's our line segment drawn between those 2 points. And if you make that right triangle like you did before, okay, and you take that midpoint and go across to get to that vertical side, and then draw down from that point to get to the horizontal side. And when you do that, you go halfway between the two x's. Okay, you go halfway on the x, and you go halfway on the y. So what we can do is we can say, okay, the x here is going to be halfway between the two x's here, okay, and the y here is going to be halfway between the two y's. Okay, so how we find the halfway point is we just take the average of the x's and the y's. So the halfway here would be x1 plus x2 divided by 2, and then the halfway for the y would just be y1 plus y2 divided by 2. So we're taking the average of the x's and the y's, or of the two x's and the average of the two y's. So that's how we get our midpoint formula here. Just take the average of the x's and the average of the y's. It doesn't matter which one's first and which one's second, as long as, if this is the first one, they're both 1s. This is the second one, they're both 2s, but don't mix up 1s and 2s. Like, this could be x1, y1, but this should be x2, y2. Okay, so there's our midpoint formula. We're getting two coordinates, an x and a y. Okay, so here's an example where we're looking at a quadrilateral, which is a four-sided figure, and it has these 4 points or vertices. P1, 2, Q is 4, 4, R is 5, 9, and S is 2, 7. Okay, and we're going to prove that it's a parallelogram, and we can prove that it's a parallelogram by proving that its two diagonals bisect each other. Okay, so what we're going to do is we have 4 points like this, and we prove it's a parallelogram by taking the diagonal. Now here's our figure. Okay, we just connect the sides like this. Okay, and we say that the diagonal, so we go across like this and across like this, and we can prove it's a parallelogram by saying that those points go straight down the middle for both of those diagonals. In other words, it's a midpoint of this point and this point, and it's a midpoint of this point and this point. Okay, so we have 4 points, and we can call them, I'm not going to put them in the right order, but P, Q, R, and S. So that's what we're going to do there. Okay, and when we say parallelogram, it means we have parallel sides here and here, and then the other sides are parallel. Okay, so that's what I mean by a four-sided figure, that is a parallelogram, that the opposite sides are parallel. Okay, so we take the midpoint, the diagonal PR, okay, and we take the midpoint of that by taking the x's and adding them, 1 plus 5 divided by 2. And then add the y's and divide by 2, so 2 plus 9 divided by 2, and that's 3 11/2. So that's the midpoint of PR. Okay. Okay, then we take the midpoint of the other 2 points, which is QS. So we did PR. It's not the same orientation, but P and R are opposite each other as before, and Q and S are opposite each other as before. So we're going to take the midpoint of Q and S, which is add the x's, so 4 plus 2, and divide by 2. Add the y's, 4 plus 7 divided by 2, and we get 3/11/2, which is the same as the other one. So we're saying that those midpoints are the same, which means that these two diagonals bisect each other. They cut each other in half. You see there's 2 marks here and 2 marks here. That means those are the same. And there's 1 mark here and 1 mark here. That means those are the same. Which means that the midpoint is the midpoint for both of those. Okay? And we did that by using our midpoint formula. And that proves that this thing is a quadrilateral, that these two sides, opposite sides, are parallel, and these two opposite sides are parallel. So whenever your diagonals bisect each other, they have the same they have a midpoint that's common, then we have a quadrilateral. Or, I'm sorry, we have a parallelogram. Quadrilateral is just a 4-sided figure. Okay, now let's look at how we graph an equation in 2 variables. Let's look at something, a quadratic, like y equals x squared plus 1. Okay, so we could say a point, an xy ordered pair, satisfies the equation if it makes the equation true. Okay, so if you plug in your xy pair into this equation, if it's true, then then that point satisfies the equation. So, for example, 310. Plug in 3 for x, and we get 3x. 3 squared plus 1 is 9 plus 1, which is 10, and that is our y. So we can say this satisfies the equation. Okay. All right. 1, 3 does not, because 1 squared plus 1 is 2, and y is 3, and we want y to be 2. So this one would not satisfy the equation. So a graph of an equation in x and y is the set of all points, xy points, in the coordinate plane that satisfy the equation. So it's all the points that satisfy the equation. Okay, so let's look at this one, 2x minus y equals 3. First thing we want to do, this is a linear equation, solve for y. So get y by itself. So if we move y to this side and 3 to this side, we get y equals 2x minus 3. And then we can look at points, plug in values for x like 0, 1, 2, 3, 4, and see what your y is by taking 2 times x minus 3. Okay, so 0 would give us minus 3 for y. 1 for x would give us minus 1 for y. 2 would give us 1. 3 would give us 3. 4 would give us 5. And if we plug in minus 1 for x, we get minus 5 for y. So here's some ordered pairs. Now, because this is linear, these points should line up. They should be collinear. Collinear means the points line up in a line. And then we can graph that. We probably don't need this many points. We could probably graph it with 3. And generally, the more points we plot, the better we can imagine what the graph represented by the equation looks like. For a linear equation, 3 should be sufficient. You don't need a whole bunch of points. For a quadratic or some curve, you might need more than that. So here's a graph of the points. We have those 6 points here, and we can see that they're collinear. They all line up. So our line looks like this. Now, when you graph these, make sure that you put the arrows here. Oops, didn't want to do that. Okay. Make sure you put the arrows here so they go in both directions. That means that line goes infinitely in both directions. Going up here and going down this way. Okay, the last thing we're going to talk about in this first part of section 1.8 is intercepts. Okay, so if we look at x-intercepts, that's where it's crossing the x-axis, where a graph intersects the x-axis. Now, when that's true, y is 0. Okay, and then y-intercepts are where the graph intersects the y-axis, and that's true when x equals 0. So think of your opposite variable, and use that equal to 0 to get the other intercept. Okay. So let's say we have this line here, it's red one, and when it crosses the x-axis, here's my x-axis. When it crosses the x-axis, my y is 0, and when it crosses the y-axis, my x is 0. So all we have to do is set the opposite variable equal to 0 to get the intercept. So for the x-intercept, set y equal to 0. For the y-intercept, set x equal to 0. And then solve for y. Okay, so here's setting y equal to 0. We'll find these points. And notice in this one, this is a polynomial function. Actually, it's more than a quadratic, but it has 3 x-intercepts. So when we set y equal to 0, we're actually going to get 3 x values. Okay. This one is actually not a function, but we'll get to that in chapter 2. Notice this crosses the y-axis twice. When we set x equals 0, we'll find these two values. Okay, so let's look at this quadratic equation, y equals x squared minus 2. Remember, it's a quadratic because you have a square on the x. Okay. So to find the x-intercepts, we set y equal to 0. This is the more difficult part of finding quadratic, is finding the x-intercepts. So when we set y equal to 0, we have 0 equals x squared minus 2. Kind of looks familiar, right? We know how to solve this, right? We would want to get the square by itself, so we just add 2 to both sides. So we get x squared equals 2. Then we can take the square root of both sides, right, to get x by itself. Remember, we do plus or minus in front of the square root of 2. Okay, whenever we take the square root of both sides. So that, square root of x squared is x. We just get x equals plus or minus square root of 2. So those are our x-intercepts. Plus square root of 2 and minus square root of 2. Okay, and then it's a little bit easier to find the y-intercepts. When we set x equal to 0, we just have y equals 0 squared minus 2. Gives us y equals minus 2. So that we only have that one y-intercept, y equals minus 2. And notice when we do find the intercepts for this equation, y equals x squared minus 2, we've actually got a pretty good picture of what the graph looks like, because here are, the square root of 2 is about 1.414, so plus square root of 2, minus square root of 2, and then we have minus 2 as our y-intercept. And we've actually got a graph that, or a few points that kind of show us what a picture of this graph looks like. A pretty good idea. We might want to check points over here, like see what happens when you plug in 2, okay, and see what happens when you plug in minus 2. And since we're taking x squared minus 2, 2 squared minus 2 would be 2, so 2 would be a point here. Okay, let's put that there. 2. Okay, and then if we plug in minus 2, we also get a 2, because minus 2 squared minus 2 is 4 minus 2. So, we might want to plot a couple extra points just to get a better idea of what the parabola looks like. But the intercepts give us quite a bit of information on that. Okay, we don't need to plug in a bunch of points. Okay, so that's it for the first part of section 1A. We'll look at circles and symmetry in the next part of 1.8b.